In today's lesson, you will be able to understand and explain why you can add, subtract, multiply, or divide each side of an equation by the same expression to get a new equation with the same solution. After finishing this lesson, you should be able to make sense of multiple ways to solve an equation. As far as our 8 mathematical practices go, we will be strongly focusing on modeling with mathematics, utilizing equations. Please go ahead and open up your workbooks to page 17, lesson 4. Please make sure to have a writing utensil while you are working on this lesson. For this first activity, which is called different equations, it is your task to figure out which of the following equations, A, B, C, or D, are equivalent to equation 1. Please pause the video at this time and explore all 4 equations and determine which of the 4 are equivalent. Once you are done, go ahead and press play and check your work with mine. If at that point you do not have the same equations that are equivalent as I do, please add to your notes or fix or adjust your notes as needed. Go ahead and pause the video now. Welcome back. Let's check equation A. If I compare equation A to the original equation, and I take a look at what's on the left-hand side of the original versus what's on the left-hand side of equation A, it appears that everything has been doubled. I can test that theory. If that were the case, then everything should be doubled on the right side of both equations as well. To work backwards from doubling or multiplying by 2, that would mean dividing everything by 2 or multiplying by 1/2. So if I divide both sides of this equation A, will I get back to equation 1? Let's see. Sorry about that interruption. So if I divide both sides by 2, let's see what happens. 2x divided by 2 gives me 1x, or simply just x. -6 divided by 2 gives me -3, or -3. And on the right side, because remember I need to balance the equation, whatever I do to the left, I must also alter the right side that same way. If I divide everything by 2, 4 divided by 2 gives us 2. -8x divided by 2 gives us -4x. So now, as you can see, the left side, x minus 3, is equivalent to the left side of equation 1, as well as the right side, 2 minus 4x, which is also equivalent to the right side of the equation 1. So therefore, equation A is equivalent to equation 1. Let's check out equation B. If I compare equation B with equation 1, and I look at the right side of the equation, I notice the 2 is missing from the right side of equation B. So how could I replace equation B with a 2? Well, I know I can simply add 2 to the right side of the equation. However, if I add 2 to the right side, I need to balance my equation, and I also need to add 2 to the left side. When doing so, on the left-hand side,
hello, okay, get to the bus now. Hello.
Again, sorry about that interruption. The announcements keep going off. So, as I was saying, if I add 2 to -5 on the left side, I still have my x, and -5 plus 2 gives me -3. Now, when comparing these two equations, we can in fact see that they are equivalent. X minus 3 on the left is equivalent to x minus 3 on the left of equation 1, and -4x plus 2 is in fact equivalent to 2 minus 4x. The two terms have just been reversed in order, which the commutative property of addition allows us to do that. So now it is evident that equation B is also equivalent to equation 1. Let's take a look at equation C. When in comparing equation C with equation 1, I can see that they have just moved the x minus 3 from the left side of the equation to the right side. So that equivalent piece is still there, it just flips sides. Now I need to be able to compare the 2 minus 4x with the left side of this equation. Since there are parentheses, I know I can take that 2 in equation C and I can use my distributive property. Let's see what happens when we distribute the 2. 2 times 1 gives us 2. 2 times negative 2x gives us negative 4x. Now we can see that both sides of equation C are in fact equivalent as well to equation 1. 2 minus 4x, 2 minus 4x, x minus 3, x minus 3. So equation C is also an equivalent equation to equation 1. Last but not least, let's check out equation D. When I look at equation D and compare it with equation 1, I notice that on the left-hand side, on the left-hand side of D, the x is missing. So I know if I want to add in an x over here, I have to balance my equation, just like my Hanger models, and add in an x on the right-hand side as well. So when doing so, let's see what happens. On the left, I have x minus 3, just like the left-hand side of equation 1. On the right, when I take negative 5x and add x to it, I get a negative 4x, which is now also equivalent to the right side of equation 1. So, as it turns out, all 4 equations, A, B, and C, are in fact equivalent to equation 1. If at this point you did not come up with this conclusion, please take a few moments and jot down the notes accordingly and add them to your workbook on page 17 to prove that all 4 equations are in fact equivalent to equation 1. A few follow-up questions for you to think about before moving on to the next activity are, which method of answering the question was the most efficient? After seeing all the ways to answer this question, which would you choose? So basically, if you were to think about starting to solve this equation for the letter x, which of these 4 equations makes the most sense to you? We have just learned that all 4 are equivalent and all 4 work, but which one is creating the least amount of work for us and is making the equation smaller? A, B, C, or D? In my opinion, equation B or equation D do just that and reduce the size of the equation and take us one step closer to solving for the letter x. What is an advantage of the equation to look like equation 1? What is a disadvantage? So when we look at these 4 examples, we can see multiple starting points. Some of them may be quicker than others, or some of us might feel comfortable with one more than the other. And that is okay, and that's the reason why there are multiple ways to start out solving equations. How is this method similar to what we did in previous lessons with balanced hangers? Well, just as I had pointed out earlier as I was solving working with each equation, I had mentioned whatever I do to the left side of the equation, I must also do to the right side, or vice versa. Just as a balanced hanger model. Whatever we do to one side of the hanger must also be done to the other side to keep it balanced. We need to remember that when we are working with equations just as much as hanger models. It's all about balance and completing the same operations to both sides. Let's go ahead and take a look at the next activity called step by step by step by step. In this activity, we are comparing Claire's work to Lynn's work. They are both starting out with the exact same equation. They choose different modalities to get to an end result. It is our task to figure out who is correct. Please pause the video at this time, analyze both of their work, and determine who you believe is to be correct, and answer questions 1 and 2 at the bottom of page 17. When you are done analyzing their work and answering questions 1 and 2, go ahead and resume the video and check your work with mine. Go ahead and pause now. Welcome back. As you are checking your as you are checking your work with mine, please make sure if you did end up with something different that you go ahead and make the necessary adjustments or corrections to your notes at this time. When I analyzed Claire's work, I noticed that her first step was to take 14x minus 2x. She can do that because they are like terms. When doing so, she ends up with 12x plus 3 on the left-hand side. She then continues to work on the left-hand side of her equation. She realizes that both 12x and 3 can be divided by 3. They have a greatest common factor of 3. So what it appears that she does next is she factors out that 3 from both of them. She divides 3 from both of these terms. When doing so, her 3 comes out front, and what's left is 12x divided by 3, which is 4x, and 3 divided by 3, which is 1 whole. So that is how she gets 3 times the quantity of 4x plus 1. At this point, she now realizes that there are 3's outside of the parentheses on both the left and right sides of the equation. So she knows, just as our hanger models, since there are 2 equivalent pieces on the right and left side, she can eliminate them. So we know a 3 outside of the parenthesis indicates multiplication. To undo that multiplication, we are going to think division, which is what Claire did. She divided the left by 3. She knows whatever she does to the left, she must also do to the right. So she divides the right by 3. When doing so, 3 divided by 3 makes 1 whole, or they divide out, and she is simply left with 4x plus 1. On the right, again, 3 divided by 3 makes 1 whole, or again, they divide out, and she is left with 5x plus 9 on the right. At this point, it appears that the 4x is gone from the left, so she must have moved that over to the right-hand side by doing the inverse of a 4x, which is a negative 4x. So, if we show Claire's work that she must have done mentally, if she takes away 4x from the left, she knows she must also take away 4x from the right. On the left, those made the 0 pair. That's how the 4x's were gone. And she was just left with 1. On the right, 5x minus 4x leaves her with 1x, or simply just x. And then she brings her 9 down. Last but not least, Claire decides to combine her constant terms, the 1 with the 9. To do this, she removes the 9 from the right-hand side. Again, she has to use the inverse operation, which would be, instead of adding 9, it would be to subtract 9. So she takes away 9. Whenever she does one thing on the right side, she needs to balance the equation and do it to the left side. On the right, she gets her 0 pair. On the left, 1 minus 9 gives her a negative 8. So therefore, according to Claire's work and steps, x should equal negative 8. Let's go ahead and take a look at what Lynn did. When analyzing Lynn's work, it looks like she took the first same step as Claire. 14x minus 2x gives her 12x. Then, however, it looks as if Lynn takes a different approach. If I look to the right-hand side of this equation, I can see that her parentheses are gone from the right side. So that means she must have distributed the 3. Remember, with distributive property, that does mean to multiply. So 3 times 5x does in fact give us 15x, and 3 times 9 does in fact give us 27. So far, Lynn's work looks great, but different from Claire's. At this point, now that I look at her towards her next step, I'm noticing that the 3 on the left-hand side of the equation is gone. So that means Lynn must have removed the 3 by doing the inverse of a plus 3, which would be a minus 3. So she knows if she's going to take away 3 from the left, she has to balance the equation, and she also needs to take away 3 from the right. On the left side, she does get her 0 pair, that's why they're gone. On the right side, 27 minus 3 does in fact make 24. Again, so far Lynn's steps are checking out. The next thing I notice with Lynn's work is that the 15x is missing from step 4 to step 5. So she must have combined her x's together, and in order to remove a positive 15x, she would have to do the inverse, which would be a negative 15x. So if she takes away 15x from the from the right, she knows she must also take away 15x from the left to balance the equation. On the right side, 15x minus 15x gives her that 0 pair, and that's why they're gone. And on the left side, 12x minus 15x does in fact give us negative 3x. Last but not least, she eliminates that negative 3 from the left side. She knows she can do the inverse because it states that it's negative 3 times x, which the inverse of that would be dividing by negative 3. She also knows whatever she does to the left, she must also do to the right. And when dividing our negative 3 by negative 3, that makes 1 whole x, or just x. And then on the right, 24 divided by negative 3 does in fact equal negative 8. So Lynn also got a solution of negative 8. So both of their work checks out. They did the math properly, but they took two different approaches. So who's correct? In this situation, yes, they are both correct. And they are both correct because even though they took different paths, they got to that same end result of x being equivalent to a negative 8. In Claire's steps, she chose to factor out a 3. Whereas in Lynn's steps, she chose to distribute the 3. Both are viable approaches that we learned about last week in last week's lesson. You could either divide out first or distribute first if you're working with parentheses. And we learned both last week, and we can see again here with Lynn and Claire's examples, that yes, both are going to work as long as we're performing the math on both sides correctly. So, how are they alike and how are they different? Well, one major thing that they both did alike was the first step, right? They both combined like terms and did 14x minus 2x. So, okay, and one example that made them different was that Claire took the dividing approach, so she divided by 3, versus Lynn, who distributed 3. At this time, please make sure to add these points to your notes in questions 1 and 2 if you did not have this already. Now let's take a look on the next page at Maya and Noah's examples. So Maya and Noah are still working with the same equation here. However, Maya and Noah did not get negative 8 for their solutions for x. They got two very different answers. Maya got got 24/7 for x, and Noah got 24/27 for x, which we just learned in the previous example that something's wrong here because we know x should be equivalent to negative 8. So let's explore both of their work and determine where they made their mistake. At this time, I'd like you to pause the video and see if you can identify where each of these individuals made their mistakes and circle it. When you are done, go ahead and press play and check your work with mine. Let's take a look at Maya's work. On the left-hand side of the equation, it appears that she started out the problem correctly and did 14x minus 2x to get 12x plus 3 on the left. On the right, it then looks like in the next step, her 5x is gone when you compare it to step 3. So when looking at Maya's work, it appears that she attempted to subtract 5x from both sides of the equation, because if I do 5x and take it away from 12, we do get 7x, except this is not possible. Maya cannot do this. And why can't Maya do this? So here is where Maya made her mistake. Maya should not be subtracting 5x, but rather, what does she need to eliminate before she can group her x's together? before she can group her x's together, she has to eliminate this 3 out front of the parentheses. Whether that would be from distributive property or dividing out, she has that option, but she must do that first before combining her like terms. Because of these parentheses, we know we have to take care of that multiplication before we can take care of the addition or subtraction piece. So Maya's mistake was she tried to subtract 5x, but first she needed to get rid of the 3 outside of the parentheses. And again, she could get rid of that 3 by either dividing everything out by 3 on both sides or distributing the 3 on the right-hand side to the 5x and the 9. Let's go ahead and take a look at Noah's work and check out where he may have made his mistake. Again, looking at Noah's work, his first step was correct when he combined 14x minus 2x to get 12x plus 3 on the left. On the right side, it appears that now Noah distributed the 3, which we talked about. That should work as long as his math checks out. And 3 times 5x is 15x, and 3 times 9 is in fact 27. So far, at this point, Noah's work looks good. It now appears that Noah removed the 15x from the right side. In order to remove that 15x, though, should Noah add or subtract it? If I look at his work, it appears that he added 15x. But we know if you add a 15x to a 15x, you're not going to get a 0 pair. Rather, you're going to get more x's. You're going to get 30 x's. So instead of adding 15x to both sides, Noah should have subtracted 15x from both the left and the right side. So when doing so on the left, 12x minus 15x is not 27x. Rather, it should be negative 3x. So this right here is Noah's mistake. Noah should have subtracted 15x from both sides, but instead he added frowny face. All right, so at this time, if you did not notice these mistakes that both Maya and Noah made, please pause the video, circle them in the appropriate places of the equation, and write down these notes to explain what their errors were. So, to wrap things up with this first activity, how do you know when a solution to an equation is correct? Well, if more than one person is getting that same solution, most likely it's correct. Another way we can check to see if it's correct is go back and substitute it into the original equations to see if it checks out or not. So the two ways I just listed are if multiple people get the same solution, then it's most likely correct. But to absolutely verify that statement, you should go back and check your work by substituting the answer for the variable back into the original equation. And then completing the math on both sides to make sure you get two equivalent numbers in the end. So if we go ahead and test this theory, our original equation was 14x minus 2x plus 3 equals 3 times the quantity of 5x plus 9. If we recall from Claire and Lynn's work, they both got x to equal -8. So if we want to double check them algebraically and make sure that it works, we're going to take -8 and replace it every time I see an x in the original equation. And our ultimate goal is to show that both sides of the equation are in fact equivalent. So let's go ahead and double check their math. On the left side, I'm going to take 14 and multiply it by -8. Feel free to use your calculator and check this work with me. And I get -112. I'm then going to do -2 times -8, and I get a positive 16. Because remember, a negative times a negative makes a positive. Plus 3. I'm going to then continue on the left-hand side and do -112 plus 16 plus 3 in my calculator, and I get -93 on the left-hand side of the equation. On the right-hand side of the equation, I know based on order of operations, I'm going to deal with my parentheses first and do 5 times -8, and I get -40. And then I need to add 9 to -40. So -40 plus 9 gives me -31. And I'm left with 3 times -31. And when I do that math, -31 times 3, I do in fact get -93 on both sides of the equation. So it does check out. Last question, who's more correct, Lynn or Claire? Well, we just proved throughout all of their work that not one person is more correct than the other. Rather, both individuals are absolutely correct. They just took two different strategies to get to the same end result of x equaling -8. Claire took the strategy of dividing by that 3 first, versus Lynn, who took the strategy of using the distributive property with that 3. All right, let's take a look at activity 2 called Make Your Own Steps on page 18. At this time, I'd like you to explore these 3 equations and do your best to see if you can solve 4x. Think about the various approaches you could start off with to help you be successful. Go ahead and pause the video at this time and attempt questions 1, 2, and 3. Once you are done, go ahead and press play and check your work with mine. If you are not getting to the same end results and getting the same solution for x that I am, please go ahead and add to your notes and make the proper adjustments or corrections as needed so that your work reflects mine. Also, I'd like you to remember there are multiple ways to approach each of these problems. So before you go ahead and change all your work, wait to see what I get for my solutions for each problem. Because just because you take a different step first off than mine doesn't mean that your answer in the end will be incorrect. Let's take a look at problem 1. So when I look at problem 1 on the left-hand side, I can tell that both 12 and 6x are in fact divisible by 3. So I'm going to go that approach and divide both of those terms by 3 first. When I divide 12 by 3, I get 4. When I divide 6x by 3, I get 2x. On the right-hand side, if I try to divide 5 and 9 by 2, I know I'm going to get some decimals. So rather than working with decimals, I know I can actually do 5 minus 9 in my numerator first, since there are no x variables that I even have to worry about on the right side. So what do I get when I do 5 minus 9? I get negative 4 divided by 2, which is a whole lot easier to divide negative 4 by 2 than 5 and 9 are. So I'm going to then divide negative 4 by 2, and I get a negative 2 on the right side. My next approach is going to be to combine my constant terms of 4 and negative 2. So if I want to eliminate the 4 from the left-hand side, I know I need to subtract it. I also know if I'm going to subtract 4 from the left, I must also subtract 4 from the right. On the left, I'm going to get my 0 pair with my 4s and negative 4. On the right, negative 4 minus 4 gets me to negative 6. Last but not least, if I'd like to eliminate that 2 from the left-hand side, I'm going to do the inverse of multiplying by 2, which is dividing by 2. I know whatever I do to the left, I must balance my equation and also do that same operation to the right. They'll divide out on the left. I'm just left with x, and on the right, negative 6 divided by 2 is negative 3. If you did not get x to equal negative 3, please pause the video now and adjust your work accordingly so it matches mine. And remember, it's not just the solution that's important, it is the work as well. So make sure your work in your book reflects this. If it is correct, then you can move on to question 2. If I take a look at question 2, on the right-hand side, I may want to eliminate that fraction. That might be my first choice. We can do this 2 ways. We know we can either distribute the 1/3, or if I want to get rid of the fraction altogether, I can do the inverse of a 1/3, which would be to multiply by 3, which I prefer to eliminate the fraction altogether. So I'm going to multiply both sides of this equation by 3. Now, the tricky part is with this, on the left-hand side, I have more than one term, so everything needs to get multiplied by 3. On the right-hand side, I already have those parentheses, so that's why I didn't have to worry about distributing it. It's already showing that property on the right. On the right, I know when I do 3 times 1, I get 3. 3 divided by 3 gives me 1 whole, or essentially, these just divide out. On the left-hand side, I now have created a problem that requires me to distribute. 3 times x gives me 3x. 3 times negative 4 gives me negative 12. So now, here is what I'm left with, and I was able to eliminate all fractions. At this point, I'd like to combine my x's. So if I want to eliminate the 3x from the left, I know I can do that by subtracting 3x to make a 0 pair on the left. I also know whatever I do to the left, I must do to the right to balance out my equation. So I'm going to take away 3x from both sides, making a 0 pair on the left. And negative 6x minus 3x gives me negative 9x. Okay. At this point, I know I can combine my constant terms, which is the negative 12 and the negative 54. My whole goal here is to solve for this x, to isolate that x. So I want to move that negative 54. So if I want to move the negative 54 from that side of the equation, I'm going to do the inverse, which would be adding 54. I know if I add 54, sorry guys, that's supposed to be a minus. I know if I add 54 to the right, I must also add 54 to the left to balance out the equation. So when doing so, when I do negative 12 plus 54, I get 42 on the left. On the right, I have my negative 9x. I have my 0 pair that cancel out, negative 54 and positive 54. And now I have one more operation to isolate for x, which is the inverse of multiplying by negative 9, which would be dividing by negative 9 or multiplying by a negative 1/9. We learned that last week as well. We're going to divide out on the left, on the right. 42 divided by negative 9 gives me negative 4.6 repeating. Okay, so in actuality, I just realized I made a mistake. Don't be mad at me. If you back it up, I noticed where my mistake occurred. Right here, I thought that this was a negative 6x, but it's not. It's a positive 6x. So at this point, again, I apologize. Let's rework the problem just from that point on. I am so, so sorry. This is what I get for writing sloppy because my equal sign tricked me and I thought it was a negative 6x. So from this point, we're still going to subtract 3x from both sides. On the left, I have my 0 pair. On the right, 6x minus 3x is not negative 9x. It is 3x minus 54. At this point, again, we're going to add 54 to both sides. We get our 0 pair on the right. On the left, negative 12 plus 54 is 42 equals 3x. And then in the end, I should be dividing by 3, not by negative 9. Sorry again about my mistake. And 42 divided by 3 is 14. So therefore, x equals 14. So I knew I made an error because I went and looked back and I realized that, oops, I added in an additional negative sign that wasn't there. I could have also checked my work in the end to realize that that original x solution I got would not have been correct. All right, if you got x equal 14, we're ready to move on to number 3. If you did not get x equal 14, please now adjust your work accordingly so it matches mine. Let's go ahead now and look at example 3. If I look at example 3, I see a negative sign outside of the parentheses. So I know just as if it were a number, I could use the distributive property. So I'm going to do just that and multiply or distribute that negative sign by everything inside. So what that does essentially is it takes becomes the opposite of every sign inside. So taking the opposite of 3x would give us negative 3x. Taking the opposite of a minus 12 would give us a plus 12. At this point, if I wanted to combine my x terms and eliminate the negative 3x from the left side, I would do the inverse and I would add 3x. I also know whatever I do to the left, I need to balance my equation and do it to the right. So I'm going to add 3x to the right side as well. I get my 0 pair on the left, and 9x plus 3x gives us 12x. Now I would like to eliminate the minus 4 from the right side of the equation and combine it with the constant term on the left, which is 12. So the inverse of a minus 4 I know is to add 4. So if I'm going to add 4 on the right side, I know again to balance my equation I have to add 4 on the left side. So I get my 0 pair on the right and 12 plus 4 on the left gives me 16, which equals 12x. And now from there I know I need to divide by 12 or multiply by a 12. Our 12s will divide out. And 16 twelfths we can most certainly reduce by 4, right? 16 divided by 4 is 4. 12 divided by 4 is 3. So I can leave my answer as x equals 4/3, or I can divide it out, and as a decimal, that would be 1.3 repeating, or as a mixed number, that would be 1 and 1/3. All three of those are equivalent answers. So at this point, check your work. Did you get x to equal 4/3 or 1 and 1/3 or 1.3 repeating? If not, pause the video, correct your work in your workbook, and then we will go on. So, some important things to note at the end of our lesson today. answering yes or no to the following question. Does each move maintain the equality of an equation? So basically, are we allowed to do each of the following moves to our equations? The first one asks, can we subtract a number from each side? Will that maintain equality in an equation? Yes, it will. As long as we are subtracting that same number from each side, we are balancing our equation properly. Can we subtract 4x from each side? Again, the answer to that would be yes, as long as we are subtracting. Sorry about that announcement again. And as I was saying, yes, if we subtract 4x from each side, we are maintaining equality on both sides of the equation. The next one asks, can we divide each side of the equation by 7? Again, yes, because if we are doing that same operation of dividing by 7 on both sides, we are maintaining equality and balance to our equation. The next one asks, can we add 5x to one side and 10 to the other? The answer to that is no. We cannot take one move on the left-hand side and do a very different move on the right-hand side. This is not allowing us to maintain equality and balance to our equation. The last one asks, are we allowed to add 4 to one side and add 5 to the other? Again, the answer is no, because adding 4 and adding 5 are not equivalent. We are not maintaining balance to our equation. They're resulting in two different numbers. If you take a look at the lesson summary on page 19 in your book, they give you another example of an equation that has been worked out. The first person who worked out this equation got x to equal 3. However, when substituting and checking their work down here, we can see that x, in fact, should not equal 3. In the end, they get two unbalanced statements. 6 is not equivalent to negative 24, so therefore x cannot equal 3. So somewhere in their work, they must have made a mistake. Can you find the mistake? Pause the video now and see if you can locate it. Just below this example, we have another student who worked out the problem correctly. When they worked it out, they realized x should equal negative 3, not positive 3. When checking their work below, using the substitution method and replacing the x values back in with negative 3, we get a balanced statement in the end. Negative 6 is in fact equivalent to negative 6. At this time, please go ahead and complete your quick progress check that you grabbed when you walked in the door today. If you have lots of time remaining and you would like to get a little bit more practice with solving equations and finding errors, feel free to watch the additional Khan Academy videos that I have posted for you on our Google Classroom page. But please make sure before you leave today's class that this quick progress check gets completed and turned into the inbox.